Hello, welcome to another Cosmology Talk. This week we have Ben Giblin, who is a postdoc at the University of Edinburgh. He's here to talk about his work with the KiDS survey, and specifically the KiDS-1000 data release that is sort of in the process of happening. The first papers have already come out. Specifically, he'll be talking about the weak lensing catalogue of shears and redshifts that is being released. We won't have any cosmological results today because the group itself haven't actually unblinded themselves. So even if I try to trick Ben into telling us stuff, he can't tell us any results. However, he will be able to tell us about what the actual cosmological observations are that will then tell us about the fundamental cosmological parameters, and specifically all about how he's checked that the catalogues themselves are robust. There's no mysterious systematic errors, that at least of the ones that we can look for a priori. Anyway, thanks, Ben. Do you want to start by telling us what it is that you did in this recent paper?
Yeah, sure. So this recent paper is about our newest data release from the Kilo Degree Survey, which is shear catalogues containing shear, which is the measurements of the ellipticities of 21 million galaxies covering an angular area on the sky of 1,006 square degrees. So that's why we've called it KiDS-1000. So this is basically our biggest data release. It's essentially is currently very soon being used to measure the most accurate cosmological constraints that we've produced in our survey. Before all that work had to be done, we first of all had to check these catalogues past a series of tests. Primarily, the tests that we looked at in the paper are to do with the modelling of the point spread function, which is, of course, very important. If you want to accurately measure the shapes of galaxies, you need to have a good control of the PSF, and also tests relating to the redshift distributions of our galaxies, which is a very important thing to get right, especially given some recent papers that we've published and other competing surveys have published that point to redshift distributions being prime candidates for things that you could get wrong that could bias your cosmological measurements. Yeah, those were the tests, and a spoiler alert, we found that the catalogues are robust, but we found some interesting things along the way about the way people have previously done PSF modelling that could be improved upon. So we try to clarify and clear the air in that respect, and we also find some things about the ways that we test the joint shear and redshift distributions in these kind of catalogues.
You've obviously, as I mentioned in the intro, blinded yourselves. Will you at some point sort of explain exactly how the blinding works?
Yes, that is a very good point. Yeah, I'll talk about blinding.
If someone is a few months from now trying to remember what it is you talked about, what are the two things that you would want them at that point to remember if they remember nothing else?
I guess a very simple thing to take away is that the new data release has gone through a lot of rigorous testing and found to be robust. But also, one of the things that we found was important in this paper was don't just copy the equations that are in other people's papers without proving them to yourself.
Awesome. So yeah, do you want to go into more detail now about why did the Kilo Degree survey get funded in the first place? What's it trying to do?
The Kilo Degree survey is a stage 3 weak lensing survey. So there's two other surveys: the Dark Energy Survey, which is primarily US based, and the Hyper Supreme Cam Subaru Strategic Program, which is primarily based in Japan. KiDS is primarily based in Europe. And yeah, the point of KiDS is not just to measure cosmological parameters through this process of cosmic shear, which is the lensing of light from millions of distant galaxies, carries cosmological information because of the lensing is caused by the large-scale structure of the universe. So it's to measure cosmological parameters from that signal, not just from cosmic shear, which is looking at the correlations that exist in the shapes of galaxies, but also the cross correlations between those galaxies and foreground galaxies. So you can use overlapping spectroscopic surveys from BOSS and Gamma, and also just combining those two measurements with clustering correlation functions as well. So you've got these three kind of probes to measure these parameters, and KiDS was sort of designed to have a lot of spectroscopic overlap, which are very important for calibrating the redshifts of your galaxies that you're measuring your signal from. And also it's sort of a general kind of galaxy survey to kind of learn more about color evolution in galaxy populations. But I'm more involved in the cosmology group, essentially. And I guess, more generally, why do we care about weak lensing as a probe of cosmology is, for one reason, it's a low redshift probe. So you're looking at the recent universe, and Planck, of course, has measured cosmological parameters to wonderful precision, but it's a very high redshift probe. So, comparing the results from these high redshift and low redshift probes is a very good way to figure out if your model of cosmology and your underlying theory of gravity are correct, or if there's something unexpected in the way your universe has evolved from redshift of 1100 to roughly today. So that's more generally why KiDS and weak lensing surveys, I think, exist. This is the survey coverage that is gone into this data release. KiDS observes in two bands, a northern band, which is at the equator actually, and a southern band. And the three colors shown here are our previous data release, which was 450 square degrees, KiDS 450, that's the blue. And the green coverage is the things that we've added since the last data release. And the gray region is going to be the end survey. So there's 21 million galaxies in this data release, and there's been quite a few improvements on this data since the previous data release. For example, there's been improvements in the way that we employ photometric redshift calibration. Primarily, this has been done by using self-organizing maps. So this is a machine learning technique where you can basically learn the mapping between the 9-band color multi-dimensional space to redshifts. So you train it on the 25,000 spectroscopic redshifts overlapping with your survey. So it learns this mapping between the photometry color space to redshift.
Does that allow you to also get a good grasp on the errors of individual photometric redshift measurements?
It's a good question. I think, you sort of aren't too concerned about the error on the estimation for individual galaxies, but the thing that is a concern to get right is the overall distribution correct. If you want to hear or read more about that, there's a paper by Angus Wright, who works in Bochum, about self-organizing maps and using them to calibrate redshifts. So that's very cool.
I will make sure to include a link in the description.
There's a little table that I've kind of gone through a few, some of the main details here just to compare the different surveys. If you look at current footprint, which is the third row down, you can sort of see the relative sizes of these surveys. So HSC is a lot smaller, but has much more precise imaging, and DES is the largest. If you look at the bands row, you can see the photometric bands used for calibrating redshifts, and KiDS has a lot more than the other surveys. And then we've all gone and inferred this parameter S8, which is in the bottom row, which is a combination of the mass density parameter and sigma 8, which characterizes the amplitude of density fluctuations. And just by looking at those numbers there, you can sort of see that KiDS measures a lower number than the other two surveys, which has led to what's being called a bit of a tension between lensing, or specifically KiDS and Planck. Basically, it's measuring the high redshift universe, and we're measuring the low redshift universe. So there's a kind of tension between KiDS. So there's two KiDS measurements here, blue and green, and those depend on the ways the photometric redshifts were calibrated. But essentially, the tension between the blue and green contours and red is at about the 2.3-ish, 2.5 sigma level. And then the other surveys measure values that are completely consistent with us, but also consistent with Planck.
Is the data in the three measurements more or less independent? Like you're not looking along similar lines of sight?
Yeah, it is independent. Yeah.
Yeah. So I mean, if you combined all three, like I guess the green, the purple, and the orange ones, it would still pull it down, right? Like if the Planck data was the God-given, this is the correct data, you'd expect purple and orange, one might be slightly below in the bottom half, and the other one in the top half. If everything's in the bottom half,
Yeah.
then eventually,
Yeah.
once you take the combined constraint, it starts to look more extreme.
Yeah, exactly.
This other kind of mild tension plays into the more famous tension, the Hubble tension, quite a lot, because a lot of the models that best fit the Hubble tension make this one so much worse that it's not winning anything. So even if this tension starts
Yeah.
off as kind of like, oh, it's interesting, but it might not be, interesting enough yet, it's still very important in trying to fit that other one.
Yeah. Yeah, absolutely. So yeah, this has sparked a lot of debate why all the lensing surveys measure a lower amount of clustering. And this debate has been reflected in papers on the archive. So there was a stressful paper for people in our collaboration, published by George Eustafio and Pablo Lemos in Cambridge. So that was kind of a paper looking at, is there statistical inconsistencies in the first KiDS data set? And I'm not sure they'd necessarily agree with our take on this, but we sort of concluded that the things they measure in that paper don't necessarily show there's anything like to be too worried about in terms of they sort of took bits of the data out and remeasured things and found you get different results, but that's, we think, just a natural thing in statistics. If you pull out, certain data points, you will get quite different measurements sometimes depending on what you take out. So anyway, not to dwell on it, but the point is that this got published, and then there was another paper from DES pointing out things in the first KiDS data release that could have been done better, and that was including survey geometry in the shape of the survey affected your covariance matrix and a couple of other things, and that was incredibly helpful for them to do that. Some of the things they published we did already know about, but some of the things we didn't. So it's been very helpful to get that. And then we published a paper that included these extra 5 near-infrared bands to calibrate our redshifts. So this is this Hildebrandt paper at the bottom. And this actually pointed to this phenomenon we find where if we use a sample called Cosmos 2015, it's a high resolution photometric survey, so it's like 30 bands. And this is the thing that DES and HSC use to calibrate their redshifts. If we use that sample to calibrate our redshifts, then the tension that we see with Planck disappears. So it kind of implies that this way we calibrate redshifts is important. And if we use the sample they used, then the tension disappears. And if we use the things we used, there's a tension. Just to highlight that there's ongoing debate about how this is done. So it kind of motivates this paper quite strongly to get your redshifts right and to get your shear measurements right. Because if you don't, George Eustafio will publish a paper saying what's wrong with your data set. So that kind of leads me on to the main point of this paper. So the paper we published just a few days ago, it kind of primarily focuses on these 2 types of null-tests. So tests just to make sure everything is hunky-dory. Null-tests of the PSF modeling. So this is modeling of the point spread function. And null-tests to look at the joint shear and redshift measurements that you've made. So to talk about the PSF modeling first of all. So this is a schematic view that's commonly used to illustrate kind of what we're doing in weak lensing and how it's challenging. So you've got an intrinsic galaxy that would look like this if you had glorious perfect imaging, and then the next panel along shows an exaggerated idea of how the shape of this galaxy is changed by lensing. In reality, the change in its intrinsic ellipticity is of order 1%, so it's not as pronounced as this. And then that image is convolved with your point spread function. So the things that go into the point spread function are like atmospheric disturbance and distortion of the light. You've got the diffraction through the actual telescope, and then you've got the detector itself, the CCD, can record the image imperfectly. And all of those factors get tied up into an effective point spread function. In case people aren't familiar with observational astronomy, it's called this because it's the function describing how the light of a point source would spread out such that that point source no longer appears like a point. It appears as something more spread out. So yeah, your image gets pixelated by your detector as well. This is sort of the challenge of weak lensing. And if you want to accurately measure the change in ellipticity of your galaxy that's caused by gravitational lensing, the cosmological signal, well, you need to know exactly how much the image of your galaxy is being changed by the point spread function, which is typically a much larger effect. So you need to have a good understanding of it. So to model this, you measure the shapes of point sources, stars, across your survey. And by doing this, you can measure how the point spread function changes as a function of position on your detector. So this is a plot from the paper. And here in the top panels, I'm showing as a function of XY position on our detector, how the point spread function would affect the ellipticity components that you measure for your galaxy. So the PSF has a sort of distinctive kind of shape across the detector, and then you would fit a model to your measurements. And in KiDS, we fit a two-dimensional polynomial across the measurements across our detector. And then you can see how good your model is by looking at the residuals. So the difference in these PSF ellipticities that you've measured in your model, and that's what's shown in the bottom panel here. And a very preliminary Null-test is to just check, is there any coherent structure in those residuals? And if there is, you're in trouble.
Sorry, maybe you said this and I missed it, but what is the difference as I go from left to right?
So you measure the ellipticities of your galaxies as a function of two components. So they're the two components. So the important thing then is it's not enough to just look at these residuals and say there's not much structure. We need to do a more thorough test than that. Another key takeaway is PSF modeling is quite hard, and there's lots of different prescriptions for how PSF modeling affects your weak lensing measurements in the literature. So one is this Powland-Henriksen model, and this is just an expression for how your PSF modeling feeds into your observed ellipticities. The first term here is like the ellipticity you would measure if you had perfect imaging and the light from these galaxies was not spread out by a point spread function. And then added on top of this is all these extra terms, like you've got the ellipticity induced by the PSF, and then TPSF is the size of the PSF as a function of position on your detector. And T-galaxy is, or T-gal is the size of your galaxy. And then delta quantities are the errors in these measurements. So the difference between, for example, the actual PSF size and the model size that you fit to the PSF. So it's not crucial to understand this. It's just basically there's this expression for how your observed ellipticities are changed by the PSF. There's another model that is kind of, it looks similar, but it's not the same. And I'll speak about how they're not the same a little bit more in a minute. But essentially, this has a bunch of other things going into it. It's got this thing M, which is a multiplicative shear bias. It's not necessarily important what causes it, but you could have some kind of multiplicative bias in the measurements of your shear. This thing in the brackets is the intrinsic ellipticity of your galaxies. And then gamma is the actual cosmological signal the lensing ellipticity that you're interested in. And then there's these extra alpha and beta terms, which are non-zero if your PSF modeling is not done perfectly. And so there's this kind of model that actually is kind of a bit more empirical. Like there's these alpha, beta, C terms that you can measure directly from the data. And there could be all sorts of things going into them that's not factored in the first model. And then there is a third kind of thing you can do, which is look at your PSF residuals, so the difference between the measured PSF and the model, as a function of position on your detector, but crucially also as a function of the flux of the measured point source. Because flux dependence in your PSF modeling is something that's not really factored in as a convention, and it is important, we sort of find. And one of the things we really wanted to clear up in this paper is that these first two models are often conflated a little bit in the literature. And the reason is that they look kind of similar. There's sort of like, oh, there's ePSF terms, there's delta ePSF terms. We'll just say that these delta T PSF over T gal terms in the top equation, they are alpha or beta or whatever. You know, when you line them up, you can just draw a line between these equations. And they're not the same, and they're not the same in a way that's important, because these alpha, beta, M terms that you can measure in the data, and particularly the multiplicative bias, you get a handle of that by doing image simulations. They're much, much larger than just using the PSF model and the size of the PSF model. So that's kind of something we've cleared up in this paper, and is kind of a lesson to not just use other people's equations for how these things feed into systematics that bias your cosmology, because there was a little bit of a conflation between previous models. So because of that, when you actually look at how these things feed into biasing cosmology, cosmological inference, and I'll explain how we do that in a second. But the sort of long and short of it is the first term you can find is harmless and causes very little damage. The second two terms are more important in that they might bias your measurements of the S8 parameter is the thing I presented before, and that's the thing we measure primarily in lensing. So the way you can look at how these bias your cosmological inference is you can basically add these effects onto your measured signal. So the signal we measure is typically it's a correlation function, which is how correlated are the shapes of all of these millions of galaxies I've measured as a function of their angular separation. And so you can calculate correlation functions from these systematic terms and add them on and run the full MCMC chain to constrain cosmological parameters and see how they bias your inference. So this is kind of just a quick look at this second model again. This expression for E observed that I've written for model 2, this first order systematics model, you can convert that into a correlation function just by plugging it into the equation for correlating it with itself, essentially. And you would get this. This is the expression for the correlation function you would measure. And so this E perfect is the thing you would want to measure. It's the thing you'd measure if there was no systematics. But there's all these extra confounding terms. So alpha and beta, they're things you can measure directly from your data by fitting this expression to your ellipticity measurements. And the multiplicative bias you can measure and get a handle on from doing image simulations of your data. And here we're showing the bias to your correlation function psi as a ratio of the measurement you would get if there were no systematics, as a function of angular separation theta, which is on the x-axis. And we measure this as a function of redshift in different redshift bins. So these different panels are the different redshift bins, where 1, 1 is a correlation of the first redshift bin with itself. and then 1, 2 as the cross correlation of the first bin with the second bin. And this pale blue band is 10% of the error on your signal.
I feel like I have to ask a really stupid question. Is the y-axis label correct? Shouldn't that mean that no bias is 1, not 0?
Oh, yeah. I think maybe there should be a delta there. So it's the fractional difference. I'm sure the referee will point that out. Yeah, there should be a delta in front of that.
Okay. Yeah. That makes sense then.
Yeah. So basically, this kind of systematic shown by the magenta line, it's often subdominant to the error on the measurement because it's within the blue band mostly. So that's kind of a good sign. But sometimes it isn't within the blue band. And previously, there has been a tendency to go, if it's within the blue band, it is fine. But what you really have to do is see how this affects your inference of cosmological problems. And our target was to have our PSF modeling not cause more than a 0.1 sigma change in SA. And this does. So that was a relief. It sort of shows the PSF modeling, at least by this prescription for the systematic, is fine. But one of the things that we did in our paper is run through these different prescriptions, because there are a few in the literature and you have to kind of check that they're all satisfied. And the other thing we had to look at was a flux dependence of your PSF modeling. So basically what I'm showing here is the error in the PSF modeling for the two components. So that's what the color bar is the error on the PSF ellipticity. And here we're showing how that error varies with the magnitude in the R band. Also binned by the chip on the CCD where these measurements come from. And this is looking at detector imperfections, basically. And what is troublesome is if you have a clear flux dependence in your errors on your PSF, because if you've got a flux dependence, flux is going to be correlated with redshift, and this is going to confound your signal, basically. And you can see that for chips 15, 21, and 30, there's clear signs of a flux dependence in our PSF errors.
Is there not a clear sign of a flux dependence for every chip? It's just that it's very small for the other chips?
Yes. Yeah, that is a more correct way of saying it. Yes, there is a low-level flux dependence in all cases, but it's particularly pernicious for these chips. And we were sort of aware that there was imperfections in these chips. Yeah, so this was actually, all kind of new stuff for me, really going into the details of detectors and learning about what causes these sorts of things, having to think about things like electrons and in their energy states again, and why does this happen? So it was quite fun to go back to this kind of thing. But yeah, you need to check if this is going to cause a problem. And so what we did was measure the PSF error as a function of this flux dependence, and then you can sort of convert that into a systematic on your measurement and then run it through your MCMC again. And the good news is, again, that it doesn't cause more than a 0.1 sigma change in your inferred SA parameter. But yeah, this is definitely something I think all surveys need to look at and think about.
And were these three chips just like broken in some way?
Yes, basically. And a collaborator of mine, I think, is working on a whole paper looking at these three chips specifically. Yeah, so I think there's some complex issues with them, but issues that the community already knows about, like the sort of brighter, fatter effect, where the CCD, when it's having a lot of electron excitement, it can negatively impact the collection of further electrons. So this has an effect of like spreading out your sources. So it's bad news. So that section in the paper's a monster, but the thing I took from it is PSF modeling is, and there's many prescriptions for how these things impact your cosmological measurements, and you need to think about all of them and make sure all the requirements are passed. And a lesson to me was double check derivations of equations in other people's papers, because they can be wrong. And yeah, flux dependent PSF errors can be a particularly pernicious problem that might bias inference. So you need to look at that as well. I'll talk about the last thing in the paper, which is a bit less of a monster than PSF modeling, is checking the joint shear measurements and redshift data that you've got are sort of accurate. And the way we've done this in a few cases in the paper is using galaxy-galaxy lensing. So this is when you look at how the shapes of your background galaxies are correlated with the positions of foreground lensing galaxies. And typically what this will cause is a tangential shear pattern, kind of shown by this schematic here. So the tangential shear is a really informative thing to measure, one for cosmology, but it can also inform you about systematics. So we developed a new test to look at this. So basically what I am showing here is the galaxy-galaxy lensing signal, often called gamma T, this tangential shear, about the positions of foreground boss galaxies. And there's about 400 square degrees of boss coverage that overlaps with our survey. And so I'm going to draw everyone's attention to the second panel down here. This is the tangential shear signal as a function of angular separation from the positions of boss galaxies all stacked. And so you get this radial pattern. So this thing is completely radial symmetric, because in this case, we've just measured this signal as a function of angle from the thing, from the galaxy, and projected it onto a 2D plane. But this new test that we developed in this paper was measuring this signal as a function of XY position in your camera frame. And that's what's shown in the top panel. And the reason this is an interesting thing to measure and a way to look at, is there some systematic, is because there could be an additive systematic in your ellipticity measurements. And that could be caused by the detector. There can be like lines of pixels that don't function well, or that kind of thing that can cause sort of a preferred direction in your ellipticities on your camera plane. And if you measure this, just the 1D signal, i.e. you just measure it as a function of angle, that additive systematic will get averaged away when you do this azimuthal averaging. But if you measure it as a function of 2D position, that bias does not get averaged away. And the difference between this 2D and 1D signal, if that has coherent structure in it, then it reveals an additive bias that you wouldn't have seen if you just measure the 1D signal, which is kind of the classic thing to do. And that's what's shown in this third panel. So basically, the difference between these two signals doesn't reveal any kind of additive bias in the ellipticity measurements. So it's a new test that we sort of advocate can be used.
What's the bottom random panel?
Yeah, the bottom is when you measure the galaxy-galaxy lensing signal about random positions on your survey. Okay. So it's a way of measuring just kind of shot noise. Mm-hmm. And then you can subtract that from the measurement too.
Oh, I see. But you wouldn't expect the 2D minus 1D to be random, because there's noise that is signal, not signal for this particular test, but it is still shearing.
Yes, yeah, you would.
So it's not bad that this doesn't look like random. I mean, it does look like random, but it doesn't look like what you've labeled random.
Yes, yeah.
Cool.
So it's a very good probe to sort of measure your shear measurements, galaxy-galaxy lensing, and it can also be used to measure the joint shear and redshift information in your catalogue. So again, I'm showing this tangential shear measured about the positions of boss galaxies, again, as a function of angular separation. And here I'm showing all these different panels correspond to different redshift bins in your tomographic sample, which is your background galaxies. So that's indicated by the T letter. And then the different redshift binning of your foreground galaxies, your spectroscopic galaxies, which is indicated by the SP number. And so the measurement from the data are these blue data points. And if your redshift estimates of your background galaxies are correct, you would expect your tangential shear measurement to scale with the ratio of the redshifts between your lensing plane and your source plane. So another way of saying that is in each of our lens bins, so in each column here, you would basically expect the tangential shear to have the same shape and it just move up.
Why is that?
Yeah, I don't think I have a short, concise explanation for why that is, but it's sort of a commonly used test of your tangential shear. I'd have to go back to the original source information on the shear ratio test, as this is called, to understand that a bit better.
So the T1 and the SP1, are they going to be roughly the same redshifts then?
They're different redshifts because you want your lenses to be very much in front of your...
No, exactly. Yeah. That was what I was going to say. I can totally understand if T1 and SP1 are at the same redshift, why there would be no correlation.
Yes. Well, yeah, I could see how that was confusing because the same numbering scheme implies similar redshift. But yeah, SP1 is sort of like redshift of about 0.1 and T1 is a redshift of about 0.7. And the blue points are what you measure from the data. And then you can fit a model to these data points that scale, with the luminosity distance between your lens and source plane. And what this means is you can see in any given column, the red line, which is the model, is the same shape. It just moves upwards. And so you should, if your redshifts are correct, fit these blue data points with that model. And you can do that and then measure the p-value and does this model fit these data points? And we find that it does. The p-values aren't massive. They're at like the 2% level. So they're consistent. It's a sort of a 1.7 sigma level. But what we find that we think is important for people to know is that there is a serious contribution to this test from intrinsic alignments. Intrinsic alignments are a confounding influence on weak lensing measurements. And this is the idea that the correlations you see in the shapes of galaxies or even the shapes in the foreground galaxies it might not be due to lensing, it might be due to some shared environment. There might be gravitational influence there, large-scale structure connecting those things. And the contribution of intrinsic alignment to this signal, the theoretical prediction, is shown by that cyan line. And so you can model this including a fixed intrinsic alignment model, and that's fine. But if you actually incorporate your uncertainty on that model into this test, the sensitivity of this test basically, it diminishes greatly. And that's something that's not typically done. So if you perform this test, including your uncertainty on this intrinsic alignment contribution to the signal, the p-values are absolutely massive and fine because your error bars are so large. And so an interesting takeaway from this is that this shear ratio test was originally developed as a test of cosmology, but in fact, it's actually weak dependence on cosmological parameters. And that's why it's a good test of redshift, or at least it would be if intrinsic alignment contribution uncertainty didn't wash it out so much. But it is being used in sort of a joint probe analysis as an extra probe you can throw in. And if you combine it with, say, cosmic shear measurements that can constrain the intrinsic alignment contribution, then this actually might end up being quite useful again. So advocating for it to kind of be used in combined probe ways if it's going to be useful in the future. So the takeaway from that kind of shear redshift test section was galaxy lensing is really useful tool for measuring shear and redshift data, and intrinsic alignments are kind of a big impact on the way this is used in the shear ratio test. And a more general takeaway from the paper is, don't worry, KiDS-1000 is a robust science-ready catalogue of shear and redshift information for these 21 million galaxies. Oh, and I actually forgot to mention this, but yeah, the paper is one of the first examples I know of a blind paper. So in the Kilo degree survey and indeed all weak lensing surveys at the moment, we blind our analysis. And that means we have 3 versions of the data, one of which is the truth and 2 are fake, and they've been derived from the original data, but they've been modified in some way. So with our last data release, it was a modification of the ellipticity information. There was a sort of random factor applied to the shear information that made the data different from the true data.
But such that it would still pass all these tests.
Yes.
Otherwise, you're wasting someone's time as they're like trying to work out what's gone wrong.
Yeah. It's a change that's applied to induce sort of back of the envelope calculation, induce something like a 1 sigma change in your end cosmology. And so that means if you don't know which data is correct, you can't tailor your analysis to get a result that is consistent with other surveys, because something you do that might push one of those data sets closer to other result might increase the tension between that result and one of the other data sets. And only one person knows which one is the truth. And for us, our external blinder is Matthias Bartelmann. He just joins a telecon to tell us at the end which one is the truth.
Oh, so you present 3 sets of contours, A, B, and C, and he's like, and the answer is...
Yeah, exactly. And usually, speaking about previous data releases, we've had one that's sort of like 3 sigma tension with Planck, one that's 1 sigma tension and one's 2 sigma tension. And we all place our bets which is correct. So this is a blind paper, which means we haven't yet, unblinded in the collaboration, but the paper was finished and our conclusions weren't blind dependent. And our conclusions are that the catalogue passes the tests. And so we actually thought it's probably a good idea to publish a paper that shows whether the catalogues pass the tests or not is not dependent on which blind is correct. If you look at the paper, you'll see loads of bits where there's red writing saying the answer for blind A, the answer for blind B, and the answer for blind C. I think blinding is very important, and all surveys should be doing some blinding to avoid confirmation bias. Maybe there'll be more blind papers in the future. And so there will be cosmological constraints with this new data set quite soon, both from cosmic shear and these combined probe analyses, which are often called 3x2 point analyses. So stay tuned.
So the next question is where to next. I guess there's the very short term where to next, which is the question that maybe everyone's waiting for, is that what does the word soon mean? And then if you want to spend some time just talking about once that's released, where does KiDS go next? Yeah,
so with regards to the unblinding schedule, I wonder if I'm allowed to say that I think I'm probably allowed to say that it is a matter of weeks to months, but more closer to the weeks timescale. And the actual cosmological results, so we have a sort of internal referee process that can take of order 2 to 3 weeks to a month. So they go through some rigorous kind of probing of internally in the collaboration before they hit the archive. And that hasn't started yet, but of order months, I think. Where next? Well, there's tons of interesting stuff to do with this data set. This is kind of a divergence from the stuff I normally work on. I normally work on non-Gaussian probes and like sort of your non-conventional probes to measure cosmological parameters like clipping, and using machine learning as well to constrain cosmological parameters. So one of the things I've worked on with a senior honours student in Edinburgh is using convolutional neural nets to constrain cosmology from weak lensing maps. And this was done on the previous KiDS data release by Yanis Flory. That's really cool. So I kind of just want to do that kind of analysis with the new data set. And yeah, there's a bunch of like new probes like density split statistics, peak statistics. These are things that I'm excited to do in the future with this kind of data, and obviously combined analysis with the other public weak lensing surveys like DES and HSC.
So yeah, the last question, outside of your own research, what do you think is the most interesting thing in cosmology at the moment?
I was trying to think of a good answer to this today that wasn't gravitational waves.
Oh, yeah. That is the most common answer.
Yeah.
And the people who've never worked on the H0 tension say that as well.
Yeah, and also the H0 tension was the other thing I obviously had in mind. So I'll try to not say that exactly, but obviously cosmology with gravitational waves is super exciting, and the ways it can be combined with other probes like gravitational lensing of gravitational waves is going to be is something that's people are looking at, and I think that's really exciting. I guess like if I had to say something different to everybody else.
Yeah. All right. I'm eagerly awaiting something different to everyone else. What will it be?
I don't know if they're exciting because they're correct. I'm not sure about how correct they are, but sort of modified and alternative theories of gravity. So I went to a really interesting talk by Neil Turok in Edinburgh a couple of years ago, and he's just moving to Edinburgh to take up a chair of some prestigious title here. And he's not a big fan of inflation at all. So he was, developing theories of cosmology to try and eliminate the need for inflation. I can't remember the name of his theory, but the analogy was used like in his theory, you explain the flatness problem, but due to it being the statistically kind of most likely ensemble, like outcome for the universe, in the same way that the sort of homogeneous distribution of particles in a room is statistically most likely. But it was very thermodynamic analogies used to explain it. This is getting back into what I work on, but I think like the accuracy with which you can make predictions in extensions to the standard model is really improving, in part thanks to machine learning and the development of emulators. So Matteo Cataneo, who works in Edinburgh, has this really interesting approach to getting nonlinear matter-power spectra predictions in essentially any arbitrary extension to lambda CDM. It involves actually just running lambda CDM simulations with modified internal conditions such that you reproduce the linear matter-power spectrum in a model you're interested in, so whatever that may be that differs from the standard model. And then you calibrate that with something called a response function that only requires the halo model is basically what goes into it, and some knowledge of the halo concentration function in whatever model you're interested in. But the point is it's cheap to compute, and you can get accurate nonlinear matter-power spectra predictions in very general extensions to the standard model. And then you can use emulators to apply that to use in an analysis. So,
where by emulator you mean like sort of interpolates between the different simulations that have been done with different sets of parameters. And I always worry about machine learning that it's what I said earlier. You don't have necessarily a strong grasp on the uncertainty as you would from a model where you know what's happening inside the black box, I guess.
Yeah, I one of the things we did when working on the convolutional neural net, applying those to weak lensing maps, we were just outputting the prediction for a cosmological parameter given this map of the universe, what's omega m and what's
without any error bar, just saying like this is the one that
yeah, but there is a way to output the full posterior probability distribution, and we've not got there yet, but that's something I'm keen to work on.
Oh, cool. Thanks everyone for watching. If you like this, please do subscribe, click the bell if you want to be notified, click like to help with the YouTube algorithms, and share the channel with your colleagues. If you have any questions or suggestions, leave a comment under the video. While you're here, you might as well go and watch another video. I think the most relevant one to this one might be Colin Hill's talk on why early dark energy doesn't solve the Hubble tension, essentially because it creates an S8 tension. So Ben has been telling us all about how those measurements are done that essentially then mean that this early dark energy model is not as good as it seems when you only apply it to the H0 tension. And yeah, thanks again, Ben, for the great talk.
Thanks for having me.